Hello viewers and welcome back to the video series on Advanced Database Management System. This is Kiran Shinde, Assistant Professor, IICMR MC Department. In this video session, we are going to discuss on the concept of serializability, and we will also talk about the first form of serializability, that is conflict serializability. Let's start. So first of all, let us try to understand what do you mean by serializability. Serializability is the classical concurrency scheme. If you remember, in my last video session, we have already discussed on the problems of concurrency control, or whatever problems arise when there are multiple transactions which are executing concurrently. And then we have also discussed certain schemes with respect to concurrency control. Similarly, this is the concept which we are going to discuss in order to see how the concurrency can be managed, can be monitored, and can be controlled by making use of this particular concept. It ensures that a schedule for executing concurrent transactions is equivalent to one that executes the transaction serially in some order. It means the motive of studying this particular concept will be to ensure that whatever schedule is given to you, and if that particular schedule is having concurrent transactions executing parallelly, then we need to check by making use of certain schemes to cross-check the result of those concurrently executed transactions, whether that result is getting matched with a serial schedule or not. Because till now we have assured that if a schedule is getting executed in a serial manner, then it will always preserve the consistency in the database, okay, and isolation in the database. So here, for us to understand whether a given concurrent schedule is imposing any consistency or is not imposing any inconsistency or ambiguity in the database, the benchmark will be what? We need to see to that the given schedule is producing a result which is equivalent to a serial schedule result. So that will be always the benchmark or the test we will be analyzing the given schedule at the back. The main objective of serializability is to find non-serial schedule. Now, non-serial schedule means what? A schedule which is not serial, which is concurrent, that allow transactions to execute concurrently without interference and produce a database state that could be produced by a serial execution. I think just before some time I talked about this. Now, what is the basic assumption in serializability concept? The basic assumption is each transaction preserves database consistency. Thus, serial execution of a set of transactions preserve database consistency. So this will be the assumption. We need to see to that every transaction which is included in that particular schedule preserves the database consistency. And when we discussed about asset properties, I have already made you understand what do you mean by preserving a data consistency constraint. Since transactions are programs, we will consider here only read and write operations. The only significant operations of a transaction from scheduling point of view are read and write. So this is the first schedule which is in this particular video session. You can see we have already discussed it rather when we talked about a concept of schedule. So here you can see there are two transactions, T1 and T2, and there are multiple instructions which are mentioned here. In T1, see the order in which the instructions are getting executed, and in T2 also you can see. What first observation you have to make is this particular schedule 3 is not a serial schedule. It is non-serial schedule. Why? Because the instructions of transaction T1 and T2, they are getting executed parallelly. It is not that first all the instructions of one transaction will be getting over and then the other will start. Okay. Now, a schedule is serializable if it is equivalent to a serial schedule. What is this line and what is the meaning of this line? Whatever schedule is given to you, if it is serial or non-serial, but that schedule, if is serializable, we need to say that it is serializable if and only if the schedule is equivalent to a serial schedule. Now, of course, we are going to see some techniques in this video session in order to analyze that if a schedule is given to you and if it is a non-serial schedule, then how to check whether that particular schedule will be equivalent to a serial schedule or not. So in order to check this, or in order to ensure the serializability, there are two forms which we are going to discuss. First form is called as conflict serializability, which we are going to discuss in this video session. And the second form is view serializability, which I will be talking on in the next session. We ignore the operations other than read and write. This is very important. Why this is getting repeated? Because we need to assume at the back of our mind that whatever operations in these schedules we are going to observe are read and write. We assume that transactions may perform arbitrary computations on data in local buffers in between reads and writes, because we cannot omit or we cannot avoid the realistic scenario that between the read and write also there are certain operations which are taking place. Okay, so here we assume that transactions may perform arbitrary computations in the local buffer in between these operations, but we will be focusing on only read and write. So let us first understand the first form of serializability, and that is conflict serializability. What do you mean by it? Let us try to understand this, the definition of conflict serializability, by taking into consideration some, I can say, notations. Instructions, you can see here II and IJ of transactions TI and TJ. So we are talking about two transactions, TI and TJ, and the instructions of TI can be called as II, and the instructions of TJ are called as IJ. These instructions conflict with each other if and only if there exists some item Q accessed by both II and IJ, and at least one of these instructions wrote Q. What do you mean by this? If there are two transactions, TI and TJ, and if the instructions of those two transactions are getting conflicted with each other, if we are saying that they are getting conflicted with each other, but in what circumstances it is possible? If there exists a data item, let's assume the data item as Q, and the same data item is accessed by both the instructions I and IJ, and out of these two operations which are going to happen on the same data item, one of the operation is right. So let's try to understand with these, I can say, actually putting some instructions in this II and IJ, you will understand. The first instruction, if you see, read Q and read Q, it means both the read operations are happening on the same data item, that is Q, by both the transactions TI and TJ. The instructions are II and IJ. Okay, but here there is no conflict. Why? Because both the instructions are trying to read the data item Q. That is why there is no conflict. Okay? So in simple language, if you want to share something and if you want to see a certain document or a certain data item which is common among more than one users, but all the users are trying to only view that particular data item or that particular part of the database, then it is not going to impose any kind of conflict, because no updation, no modification is going to happen if you are only viewing. Okay, and that is why two read operations, okay, belonging to two different instructions of two transactions never conflict. Coming to the second pair of instructions, II is equal to read Q and IJ is equal to write Q. Now they conflict. Why? Because one of the operation is right. But how? Soon I'm going to explain to you. This kind of conflict is called as temporary read problem. When there are two operations going on to the same data item and those operations are belonging to two different transactions, then whatever problem exists, okay, that problem is called as temporary read. Similarly, if you observe the third instruction pair, there also, if you see, there is one operation which is right onto the same data item, the two instructions are belonging to two different transactions, then we say that again there is a conflict, and this problem is called as dirty read problem. And the last instruction pair, if you observe, again the data item is same, instructions are belonging to two different transactions, and of course there are more than one write operations which are happening onto the same data item, right? So again there can be conflict. Okay, And this particular conflict is called as lost update problem or blind write. Now I'm going to make you understand with an example how actually we can say that this kind of conflicts arise. Okay, let's see. So first of all, let's try to understand with this particular problem by taking into consideration two transactions, T1 and T2. If both II and IJ are read instructions, then the order of the instructions does not matter. But we say that II and IJ, the two instructions, conflict with each other if these operations are by different transactions. Now, this particular point is very important to be understood because like later on when you start practicing, and if you just tend to forget that these two operations which you need to check whether they are conflicting with each other are belonging to same transaction or different transaction, then it will be very difficult for you to analyze and monitor whether there exists the conflict serializable schedule or not. Okay, and that is why this point is written here that both the transactions should be belonging to different transactions on the same data item, and at least one of these should be right. Okay, so these 2 points you have to remember whenever you are asked to check whether the instruction pair is a conflicting instruction pair or not. Now let us try to understand the problem WW. It means both the instructions are trying to write the same data item and both the instructions are belonging to two different transactions. Consider this particular schedule, schedule number 4. Here T2, that is transaction T2, is performing a write B operation, okay, without read B after T1 has modified that particular data item B. Okay, so first of all, let us try to see the sequence in which the instructions are getting executed in this particular schedule. First of all, T1 has read the data item A. After that, T2 has started. T2 has read the data item A. After that, it has modified data item A. Then it has read the initial value of data item B. After this, again T1 started its with its leftover part, and now it is trying to modify the value of data item A. Okay, so here also if you see the value which is already modified by data item, rather transaction 2, the transaction 1 is trying to modify that particular value of data item A. After that, it is trying to read the data item B value, and then it is modifying the data item B. After its modification, that value is not read by transaction T2, but rather T2 is trying to modify the same value of data item B. Okay, so if you see here, whatever line is mentioned, as T2 is performing write B without read B after T1 has modified the data item B, so write B of T1 and write B of T2 are conflicting with each other because after the data item B is modified, again T2 is trying to modify the value of the same data item. So here you can see this also. Okay, so this write A has been executed by transaction T2, and again T1 is trying to modify the same data item here. Okay, so these are WW conflicting pairs, that is write conflicting pair. Okay, so here the problem will be lost update problem because no transaction will be able to preserve the final modification in the database. Okay, because this overwriting is happening here. Now let us try to understand what you mean by RW problem. Okay, so if one of the pair, one of the instruction pair is write, one of the instruction in the pair is write. Consider schedule 4. Now here also we are going to consider this particular schedule. I will just go to that schedule and explain you what exactly problem is shown in that particular schedule. As write A of T1 has been delayed, read A of T2 reads the initial value of A instead of updated one. Okay, let us try to see. So first of all, we will go to that particular schedule and try to observe this RW problem, okay, or temporary read problem. Okay, so let us have a look at this particular schedule. What is happening here is read A is the first instruction in transaction T1. After that, what transaction T1 has done? It has updated the value of A. It has deducted $50 or maybe amount 50 from the initial balance of data item A. Now, after it has done this, before this particular updation is stored into the database, the write operation of T1 is delayed and T2 has started in between, and it has started reading the initial value of A. Okay? Now, realistically, what should have happened is this particular updated value of A should have been stored into the database, and this updated value should have been read by transaction T2. But what has happened is the write operation of T1 has been delayed, and in between T2 started, T2 read the initial value of A. Again, it has done some kind of modification onto A, and then it has written back A. After that, it has read data item B. Okay, and then if you see here, after it has read the data item B and after it has modified data item A, the operation of T1, which was expected to be happen here, okay, immediately after it has modified A, it has been delayed, and now it is updating, or it is trying to store the value of data item A, which it has updated. Okay, and then the rest of the operations are happening here. So what is the problem here? If you just see, if we just again go back to our slide where we are discussing about this RW problem, let me just migrate to that particular slide so that I will explain you. So here what is happening is write A of T1 has been delayed, as I already mentioned, and as I already explained to you. Read A of T2 reads the initial value of A instead of the updated one, and hence read A of T2 conflicts with write A. Why? Because T2 is trying to read the initial value of A, but whereas it has been already modified by T1, but because the T1's write operation has been delayed, the value which is read by T2 is not the correct value. Okay, so this problem is called as temporary read problem. Fine. Now let us try to understand the third problem, that is WR problem, which is called as dirty read. Again, I have taken into consideration two transactions, T1 and T2. First transaction has started reading the value of data item X, then it has done some modification, it has modified that value and written back that particular value, okay, to the database. After that, T2 has started. Now, T2 has read the updated value of data item X here. If you see, okay, if you see this particular instruction in T2, T2 has read the updated value of data item X. Okay, and then after that, it has modified some something, or rather it has applied some operation in order to update the data item X and then written back that particular value with the help of write operation. Okay. Now, after that, the leftover part T1 has started, but it so happened that at this particular moment of time, T1 failed. And it can happen like because of any kind of a reason, logical error or software error or any hardware error, right? Any kind of failure can happen in between. So let us assume at this particular moment of time, T1 has failed. Now, what will be the effect of this failure? T1 fails and must change the value of X back to its old value. Why? Because here it had modified that particular value, but before it commits, before transaction T1 commits and successfully stores the updated value to the database, it has failed in between. So realistically, what should happen? It should roll back and start with its initial value of X. Okay. But then in between, what has happened is, meanwhile, T2 has read the incorrect temporary incorrect value of X. Why? Because that time when T2 tried to read the value of data item X, T1 had modified it, and that modified value T2 has read. Okay, so because of this, what will happen is this particular value, whatever T2 has read, is not existed in the database at all, because T1 will be rolled back since it is failed. Okay, and that particular read, which is done by transaction T2, will be called as dirty read. Okay, so this is third problem, or this is third conflicting pair in your schedule. Okay, so which is called as WR or dirty read problem. Now, as I already mentioned, that how are you going to observe that whether the given instruction pair is conflicting with each other or not? Okay, and once you come across any schedule which is having such conflicting pair, then what should be the conclusion that we are going to see now? If a schedule S can be transformed into a schedule S dash by a series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent. Now, what do you mean by this? Up to this particular point, you have understood that, okay, what instruction pairs are called as conflicting instructions. Okay. Now, after that, what we need to understand is whatever schedule will be given to you, okay, if you can transform that particular schedule into a schedule by swapping certain non-conflicting instructions and then converting into a serial schedule, then we can say that the given schedule is conflict equivalent. And then we say that it is conflict serializable if it is conflict equivalent to a serial schedule. Okay, we will see one example. But first of all, let us understand what you mean by non-conflicting instruction. Obviously, non-conflicting means what? If both the operations are happening onto the different data items, that can be a non-conflicting instruction. If both the instructions are read instructions, both the operations are read operations, and if they are happening onto the same data item, still it is non-conflicting instruction. But apart from this, if you come across any kind of an instruction pair, then it will be conflicting instruction pair. Okay, let us try to understand with an example. Here you can see that if it is a simple schedule, okay, a small schedule having two transactions T3 and T4. Now here you can see we cannot find an instruction pair which is non-conflicting. Why? Just cross check. If you say read queue and write queue, of course, if you are checking whether a pair of instruction is conflicting or not, please do not forget both the instructions should be belonging to two different transactions. Okay, so we cannot check read queue and write queue like this. We need to check instruction from one transaction and the instruction from another transaction. Okay, so read queue, write queue. Yes, these are conflicting instructions. Just before some time we saw one of the operation is write RW problem. Okay, if you just just go ahead, write queue. Yes, these two instructions are also conflicting with each other because they are functioning or they are applying the right operation onto the same data item. Okay, so here apart from these two instruction pairs, there is no other pair which is existing, right? So this particular schedule cannot be transformed into a serial schedule because there is no way we can swap any non-conflicting instructions because there are no non-conflicting instructions in this schedule. Okay, so we are unable to swap any instructions here, non-conflicting instructions here. So this can be this particular schedule cannot be transformed into a serial schedule. Now we will see one more example with which we will understand how a schedule can be transformed into a serial schedule. Let's go ahead. But before that, again, the thumb rules. Two operations are said to be conflicting if all the conditions satisfy. First, they belong to different transactions. Second, they operate on the same data item. And third, at least one of them is right operation. Now, we will be taking into consideration one example here. Okay. Directly, I will take you to the schedule. Yeah. So here, consider a schedule which is having two transactions, T1 and T2. Now, a serial schedule T1 followed by T2 can be formed out of this, but how? We will observe. How can be done? How this particular schedule can be transformed into a serial schedule? Just before some time I told you, we need to identify some non-conflicting pair of instructions, the swap of which can transform the schedule into a serial one. Okay, so we will slowly try to understand and observe this particular schedule and initiate the swapping of non-conflicting instructions. Okay, so let's start. So first of all, we saw that the instruction in T2, that is read A, okay, and the next instruction in T1, that is read B. If you just observe this pair, yes, these are not conflicting with each other. These two operations are not conflicting with each other. Why? Of course, when there are two read operations, then there is no problem as such. But on top of it, the read is happening on two different data items. Okay, so this is 100% non-conflicting pair. So we can swap this particular pair, and swapping means what? We are just changing the position of these instructions in the sequence. Okay, so this read B will go up and this read A will come down. Okay, so that will be the first swap. Next instruction pair which is not conflicting is this next. Next is WA and WB. Okay, so here also the even though both the operations are right, but the right operations are happening on two different data items. So 100% this is non-conflicting instruction pair. So again, with the swap of these two instructions, what we will get, this WB will go up one level and WA will go down one level because we are swapping, we are interchanging their positions. Okay, so after swapping these two instruction pair, what we get is Okay, just observe, this is purely serial schedule. T1 followed by T2. Why so? Because all the instructions of T1 are getting executed first, and then the instructions of T2 are started. Okay, so this is a pure or strict serial schedule. Okay, T1 followed by T2. So what is the takeaway? Whatever schedule was given to us, we could observe some non-conflicting pair of instructions, and we swap those non-conflicting pair of instructions and transform that schedule into a conflict or into a serial schedule. And so we can say that the given schedule is conflict equivalent to a serial schedule.